Welcome back. We're doing applications of derivatives review today. It's all the same derivatives you've been doing, but actually now applying them. So a really quick and easy one, we've done tons of these. It says find the equation of the line tangent to 3x squared plus 4 at x equals 2. We're going to go through a bunch of examples like this. As always, if you feel you know it and don't need to spend time on it, skip ahead in the video. Easiest way to do that, I actually think, is use that little speed option on YouTube where you can speed it up or slow it down. You can play this at 1.5 or double speed. I find 1.5 works actually pretty well for just looking through something you already know and keeping up with it, and it makes it run faster. You can get stuff done a little bit faster. And then slow down to 1 speed. You can even go to like half speed on stuff that it's like, oh, wait a minute, it's been a while since I've talked about this. But I'll run through this example quick. If you want to find the equation of a line tangent to anything, well, a tangent line is a line, and a line just requires two things. It requires a point, and it requires a slope. So I need to find a point of this line, and I need to find a slope of that line. The point, I know the x value. Point is happening at 2, so the point is going to be 2 comma something. To find the something, just take the 2 and plug it into there to see what y is whenever x is 2. So plugging a 2 in there, I'd have 3 times 2 squared. Well, 2 squared is 4, so 3 times 4 is 12, plus 4 more is 16. So I've got the point 2 comma 16. Slope, we know we're in calculus. We know how to find slope in calculus. To find slope, you need to find the derivative. The derivative is 2x. But particularly, I want to know the slope at x equals 2. So plug a 2 into this thing. At x equals 2, y prime. Sorry, y prime is 2x, so 2 times 2 is 4. I'm just trying to think of how I wanted to type that in there. So I've got a slope of 4. Got a point of 2 comma 16. The equation of any line is just y minus y sub 1 equals slope times x minus x sub 1, right? That's point slope form of a line. Plug your stuff in, you got it. In this particular case, it would be y minus the y coordinate, which is 16, equals the slope, which I said is 4, times x minus the x coordinate, which is 2. That is the point slope form of a line. Yes, I could make it a nice y equals line, get it in slope intercept, but that's never actually necessary. Once you got the equation of a line, it's an equation of a line. Unless you've got a good reason for simplifying it, you can just leave it like that. Next one. This one gets people because it suddenly asks for a linearization. Notice it's the same equation, same point. Find the linearization of 3x squared plus 4 at x equals 2. Some of you guys might remember, is this really any different than finding a tangent line? Answer, no. If you ever see a question on the AP exam asking for linearization, it's literally just asking for the equation of a tangent line. Same exact problem, same exact answer. The reason it's called a linearization is if you have a curve and you want to find like a linear representation of that curve at a particular point, well, that linear representation would just be a tangent line, the line that goes through the same point on the curve and has the same slope. It's a tangent line. So this is the exact same thing. So I'm going to just write a note on that. Finding the linearization of a line is the exact same thing as finding the tangent of a line. Nope. Tangent line of a curve. Linearization of a curve. Right. Linearization of a line would be kind of silly as it is already linear. All right, moving on. See if I can get this done in time. Mean value theorem. If f is continuous on a closed interval and differentiable on the open interval, there is a number c in that interval such that f prime of c equals f of b minus f of a all over b minus a. You might recall this mean value theorem literally comes from the slope formula. What it's saying is if I've got some graph, just make it look like this, whatever, like that. And if it's continuous from A to B, and also differentiable during that entire interval, right? It's saying there is a number within that, somewhere in there, such that the instantaneous rate of change is equal to the average rate of change. Or another way of saying that, there's a number such that the instantaneous slope is equal to the average slope. So if A was right here and B was right here, what this theorem is saying is that somewhere in that interval, there is a point where the slope is the exact same as the slope that connects those two endpoints, the average rate of change, right? So if I connect those two endpoints, I can see that I've got a slope like that. Let's say that's, I don't know, 1/4. Somewhere in here, there's going to be a C that also has a slope of 1/4. I could even say, it looks like it's probably right about there-ish maybe, right? A little bit up, looks like there. It might have a slope that's the same, it's parallel. So I would have a C there. This one actually has a second one. I'll call this one C1. Another one looks like maybe right about here. There's another one there. Mean value theorem just guarantees there's going to be at least one C that has that instantaneous slope. Big thing with mean value theorem, it only applies if your function is both continuous and differentiable, right? If that doesn't happen, mean value theorem doesn't apply. I've seen questions both where it does apply and where it doesn't, so make sure you understand when it does and when it doesn't apply. Quick examples of both. As soon as I can get out of this mode back to here, hold on, sorry about that. All right, quick example of both. Here, given that f of x equals 10 over x minus 1, explain why the mean value theorem does not guarantee there exists some c within that interval such that f prime of c is 1. Whenever you see something like that saying, hey, there's some c such that the f prime of c is 1, that's going to be a mean value theorem question. First thing I would do is just make sure you check that it would apply. In this case, the mean value theorem does not apply because my interval is from -4 to 3. And over here, there is definitely a problem with that. When you put a 1 in, which is in that interval, you got 10 divided by 0, which is not continuous. Since it's not continuous in the interval, the mean value theorem does not apply. Maybe there's a C, that's where the derivative is equal to 1. Maybe there's not. I just don't know. So the mean value theorem does not apply because f of x is not continuous at x equal to 1, which is in the interval -4, 3. Right? That's a problem. I can't rely on the mean value theorem to help me out with this. Next one, exact same type of question, but this time it does apply. It does apply because my interval is now from 2 to 6. That problem at 1 is not within that interval, so I'm good to go. However, there are two things I gotta check. So first is that it's continuous and differentiable, so I'm gonna mention that. F of x is continuous and differentiable over the interval 2, 6, right? But then there's that second part of the mean value theorem that has to work too, right? And that second part of the mean value theorem says, if that happens, this is true. So we better check that that f prime of c was actually equal to the average rate of change. So then that's just checking that. This is claiming that there's going to be some f prime of c equal to -2. So let's just check. We're going to do f of 6 minus f of 2 all over 6 minus 2. Kind of thicker line than I need, but it'll have to do. All right, so if I do that, f of 6, plug a 6 in there, I've got 10 divided by 5, right? 6 minus 1 is 5, 10 divided by 5 is 2. So then it's up with 2 minus, put a 2 in there, 2 minus 1 is 1, 10 divided by 1 is 10, so I get 2 minus 10 on top. On the bottom, have 6 minus 2, which is 4. Again, that fraction bar is annoying me, but I'm going to deal with it so I don't waste time fixing it. 2 minus 10, that's negative 8. So that's negative 8 over 4, which is indeed equal to negative 2. That part's important because, right, the mean value theorem guarantees that the instantaneous rate of change is equal to that thing. And if this said something other than negative 2, right, if that was like a negative 4, I'd be like, oh, no, the mean value theorem only guarantees that this average rate of change is going to be equal to negative 2 somewhere, or the instantaneous rate of change is equal to the 2 somewhere. So whenever you're doing an mean value theorem problem, you got to show both those parts. You show first off that you know it's continuous and differentiable. You show that the average rate of change is equal to some number. In this case, they gave it, but I got to show it. And then you can make your conclusion. Thus, by the mean value theorem, there must exist some C within the interval. I'll just say within 2, 6, such that f prime of C is equal to negative 2. Justifying mean value theorem questions can get long, but the big things you got to look for: notice that it's continuous and differentiable. Find that average rate of change, f of b minus f of a all over b minus a, and then you can make your conclusion. First derivative test. That's just finding maximums and minimums. We've talked about this a lot. These are justifying things, right? We talked about justifications, and you have to make sure you write these correctly. If you know that your derivative changes from a positive to a negative at some point, right? That's changing from a positive slope to a negative slope, positive slope to a negative slope. Then you have a maximum. So I know I've got a maximum there. Let's see if I can just type. Yeah. If your slope changes from negative to positive, you have a minimum. And I just made a mistake. I really recommend you don't. Whenever you're talking about, you're recognizing that slope's changing from a negative to positive, that gives you minimum. Don't ever call it slope, call it the derivative, call it f prime, like name it. When f prime changes from negative to positive, you know you have a minimum. Don't start using the word slope pretty much ever. You start using the word slope, you're going to mess something up, because slope can apply in all sorts of different ways. So when you're talking about the derivative, use the proper terminology. Same thing here. If f prime does not change signs at C, if it was positive and it's still positive or anything else, then there is no maximum or minimum at C. There is no max or min at x equals C. All right. Next slide, concavity test. You guys should know this. It has to do with the second derivative, tells you concavity. If the second derivative is positive, you are concave up. In other words, got that upward facing curve. If the second derivative is negative, you are concave down. You have a downward curve, right? If you are switching from a from a downward curve to an upward curve, right? Right at that point where you switch, that's given a name. It's called an inflection point. So remember that those are inflection points there. And remember that's going to occur when the second derivative changes signs, which should make sense because that's when I'm changing from one concavity to another. So right there where those concavities change signs, that point is given a name. It's called the inflection point. There is a second derivative test for extrema. Extrema being maximums and minimums. People tend to forget about this one. They tend to especially confuse it with a test for concavity because it has that word second derivative in it, and we use second derivatives to find concavity. Second derivative test, though, is actually a way of talking about a maximum. It says if f prime of C is 0 and the second derivative is greater than 0, then you have some kind of maximum or minimum. That's your first derivative. Being 0 means you got a horizontal tangent, right? If you've got a horizontal tangent and your second derivative is positive, that means you got a horizontal tangent and you're concave up. If you're concave up and you got a tangent right there that's horizontal, that means you must be at the very bottom of that curve. If you're at the bottom, that means you've got a minimum. So if you know the first derivative is 0 and you know your concave up, you have a minimum value, minimum point. Same thing the other way around. If your first derivative is 0 and your second derivative is negative, that means you're concave down with a horizontal tangent. That means you're at the very highest point of that curve, which means you are at a maximum. All right. So couple quick examples with some justifications, because that's the thing we need to be really clear about. It's not a hard example. Just one to kind of emphasize. Don't forget how to justify. This one says find where all local maximums occur. They give us a function. So I say, all right, no problem. If I want to find a maximum, I need to look at the derivative and see when it changes sign. So first step would be to find the derivative. In this case, the derivative would just be 3x squared minus 3. Particularly, I care about where the derivative is 0, right? Or undefined, where I have critical points are where it's 0 or undefined. This thing is never undefined, so I really care about when it's equal to 0. So I will care when 3x squared minus 3 is equal to 0. Whenever you set the derivative equal to 0, don't just do it in your head and say x equals whatever, right? In this case, plus or minus 1. Don't do that. Like, write this step in, especially on free response, which this year's exam is all free response. They're looking for you to set the derivative equal to 0. If you skip that step and just go straight to the answer, saying x equals 1 or x equals -1, there is a decent shot that they're going to be like, no, you are not getting that point because you didn't say where those numbers came from. Like, why is it 1 or -1? There's nothing about this that says x has to be 1 or -1. The reason x has to be 1 or -1 is when I look at that, I can say, oh, that's my derivative. To find maximums or minimums, I care when that derivative, 3x squared minus 3, care when it's equal to 0. So write that step in every single time. If you want to do the steps to show how you get your answers after that, more power to you. If you can do it in your head, I don't care, but write that step. Like, that's important, right? Then yes, you want to get x by itself. You add the 3 to both sides, divide by 3, you get x squared equals 1, which yes, x equals 1 or -1 are my critical points. Just make sure you have this step in there. That's really important. All right. So those are my critical points. I've got to tell if those points are maximums or minimums. That's where we tend to use a sign chart. So I'm going to pull us out on my sign chart. I am going to put those critical points in here. There's a -1, there's a +1, and then I just plug it back into my derivative, and I find when my derivative is positive or negative. If I wanted to make my life easier, when I do that derivative, I'll factor it first. This factors into 3 times x squared minus 1 equals 0, which then will factor into 3 times x plus 1 and x minus 1. Not only is that a way of solving it, right? There is one answer, there's the other way. But if you factor it, then it makes finding these positives and negatives a lot easier, right? If I put something more negative than -1 into this thing, I'll have a negative number times a negative number, right? Like if I put -5 into there, it'd have to be a -4, and that'd be a -6. A negative times a negative is a positive. So I definitely would get a positive value for all x values here. So that'd be a positive value for my derivative. Plugging something between -1 and 1 in there, well, that'd be like 0. If I plug a 0 into here, that's positive, that's negative. Positive times a negative is negative. Plug something more positive than 1 in here, like 10. Put a 10 in there, that's positive. Put a 10 in there, that's positive. Positive times positive is a positive. And then I want to find all local maximums. I know those happen when I change my derivative from a positive to a negative. So I say, oh, there it is right there. And then I just answer the question, making sure I am justifying the answer. So there, let's move that there. There we go. There is a local maximum at the point x equals -1 because f prime, you can see f prime of x, I'll put that space in there so it's more clear. F prime of x changes from a positive to a negative at x equals -1. When justifying a maximum, having that from a positive to a negative is essential every single time. If you're trying to justify maximum, f prime changes from a positive to a negative. Done. The only other thing I have to mention about finding maximums or minimums is be careful on if they have a closed interval. Like if this said find where all maximums, or especially if it said find, let's pretend this says find the absolute maximum over, let's say, -8, 12. I don't care, whatever. Then I would want to find which one is my absolute maximum, because if I looked at this graph, I can see at -1, it's got a local maximum. At 1, it's got a local minimum. But that means it looks something like this, right? Local maximum, local minimum, and then back up, right? And if this is at 12, the real question is my absolute maximum here at -1, or is it at my endpoint over here, wherever 12 is at, right? Did it go far enough that this maximum got taller than that? So if it ever does talk about an absolute maximum or give you some kind of endpoints, then check those endpoints and see which one is actually the larger maximum, the higher maximum. All right, I'm gonna get rid of this because that wasn't the original question. It was just a side note, which was probably helpful. And let's move on to the next page. All right, find where all inflection points occur. Inflection points are where I change concavity. So that's just looking at the second derivative. It shouldn't be too bad. We already found the first derivative, f prime of x, we said was 3x squared minus 3. So the second derivative would be just the derivative of the derivative. That'd be 6x. Same thing, I care where the second derivative is either undefined or where it's equal to 0. 6x is never undefined, but it does equal to 0 someplace. And again, write that step down. Don't just say x equals 0 and assume I know what you're talking about. Set the second derivative equal to 0 and then show what x must be. So I care when the second derivative is equal to 0. That happens when x equals 0. So that's my critical point. You can make a sign chart again. The reason the sign chart's important is at that critical point, on one side, the derivative is going to be some sign. On the other, it might be the same. Like if this is a negative on this side and a negative on that side, then that's not an inflection point because it didn't change. In this case, if I put in something less than 0 into here, right, that's definitely a negative value, so that's right. If I put something more than 0 into there, that's positive, that'd be a positive value. So the second derivative does change from a negative to positive, so it is an inflection point. Just make sure to check that. All right, so then yeah, let's write that one down. F of x has an inflection point at x equals 0 because, and again, say why, f double prime of x changes sign at x equals 0. I don't have to say from positive to negative or negative from positive because any change in sign is going to be an explanation point. Just make sure you say f of x has that inflection point, right? I know f has the inflection point because f double prime changed sign. It's not that f double prime has an inflection point. That's not true. F has the inflection point because the second derivative of f tells me about the concavity of the original. All right, we are just about done. one last question on related rates, and then you'll be free to work. Related rates is not too terribly hard, especially if you can just identify it. Basically, if they ever give you a problem where they're talking about different types of rates, right? Like say, hey, the length is increasing at this rate, the width is decreasing at that rate. That's going to be a related rates question. The way to solve all related rates question is just start with some equation that relates your variables, find the derivative, and plug in what you know. In this case, let's read this thing. It says the length of a rectangle increases at a rate of 0.5 centimeters per second. The width decreases at a rate of 0.5 centimeters per second. One increases, the other decreases. All right. At a time when the length is 10 and the width is 7, what is the rate of change in the area of the rectangle? Since we're talking about rectangles, sometimes it can be really helpful to draw a picture, especially if you have time. If you don't have time, it's not necessary, but I'm going to. And it's asking about the rate of change in the area. So I've got to compare area to length and width. I'm like, I know how to do that. The area of a rectangle is equal to the length times the width, right? However, this is asking me for the rate of change in the area. Well, if A is area, the rate of change would be how fast that area is changing with respect to time, t. So I really want dA dt. I want the derivative of A with respect to t. So I take the derivative of everything with respect to t. Derivative of A would be dA dt. That'll equal the derivative of this thing. That's a product, so I got to use product rule. Product rule says first times the derivative of the second. First is length, so length times the derivative of the second. Second is w, so derivative of that would be dw dt. Plus second, which is w, times the derivative of the first. Derivative of length is dl dt. Right? And then you just plug in the things you know. In this case, I don't know dA dt. That's what it's asking for. So I'm like, I don't know what that is. So I'm going to just leave that dA dt. That'll equal length. I know what length is. Length is 10. So 10 times dw dt. That's the rate of change of my width, right? That's how fast w is changing with respect to time. And they told me that the width is decreasing at 0.5 centimeters per second. So that would be negative 0.5, because decreasing would be a negative change, centimeters per second. Plus, the width is just 7, all right, 7. Times dl dt, that's a change in length, and they told me that's increasing at 0.5 centimeters per second, so 0.5 increase. All right, that's my dA dt. In this case, 10 times negative 0.5 would be negative 5, plus 7 times 0.5 would be 3.5. If I add those together, I get a negative 1.5. That's the rate of change in my area. That's a really weird number standing by itself, so it's got to have a unit. Let's take a look. These were measured in centimeters. Those were measured in centimeters per second. This is area. This is going to be changing in square centimeters per second, because square centimeters are a measure of area. Square centimeters per second, or centimeters squared per second. All right, that's how fast my area is changing. You can always literally put in those units to find out, right? Like if I wasn't sure, I can look at these numbers and I could say, well, that 10 isn't just a 10, that's 10 centimeters, right? So if I did 10 centimeters, I actually put my units in there and I multiply, that's not just a negative 0.5, that's a negative 0.5 centimeters per second. 5 centimeters per second. I can see that multiplying the labels works out just the exact same. Centimeters times centimeters is centimeters squared divided by seconds, right? So if you're not sure about the label, literally put the labels of your units right in here. You'll get out the right label. One thing just to make sure, if these are measured in centimeters, better make sure that's measured in centimeters too. Otherwise, if this was in centimeters and that was in meters, my labels would have been centimeters times meters per second, which is a weird unit. You probably want to convert it. All right, that is it. See you next time.